with direct search method. All right, there are two methods that we have discussed. Actually, there are lots of methods in direct search method, but we discuss only on Fibonacci and golden search algorithm. So as for today, we are going to proceed with interpolation method. Okay, interpolation method. There are two methods in interpolation methods, which are quadratic and cubic interpolation, right? So I have shared the note with you in the e-learning. Okay, so the note consists of quadratic and also cubic dividend cubic interpolation. So there are two methods that we're going to discuss in this interpolation methods. Okay, so let's start with the quadratic interpolation method for today. Right, so now all of you knows how can we find the quadratic function, right? All of you knows about the quadratic function, and remember in plotting the quadratic function we have what? We have the shape of the quadratic function where we want to find the minimum or maximum here. Okay, right, so that's why this quadratic is another method or another approach that we can use in order to find our optimal solution. Okay, so let's see about the theorem first. Okay, if we know the values of fx, okay, at three distance point of x1, x2, x3 to f1, f2, f3 respectively, then we can approximate fx by the quadratic. So if the quadratic function here at three distant point x1, x2, x3 will give you f1, f2, f3, then the quadratic function is represented by ax squared plus bx plus c, where we can have A, B, and C here by solving this. Okay. Right, ax1 squared plus bx1 plus c equals to f1, ax2 squared plus bx2 plus c equals to f2, ax3 squared plus bx3 plus c equals to f3. So this is the general form of quadratic function, and if this quadratic function can give you three distinct points of three distinct value, then we can find A, B, and C here by solving this by using a matrix system. Okay, so let's form the matrix system from this quadratic function. So we have x1 squared, x2 squared, x3 squared, x1, x2, x3, 1, 1, 1. Okay, and we are going to find what are the values of A, B, C here. Okay, so the solution of A, B, C here is given by this, where the solution of A, B, and C here comes from the solution of the matrix here. All right, where we can solve this by using Cramer's rule. Okay, so you can obtain the value of A by calculate the determinant of what? Substituting F1, F2, F3 in the first column, right? Remember Cramer's rule? Divide by the determinant of matrix X1, X2 there. Okay. This is the solution for A. All right. So now, as you can see, this x3 minus x2 times f1, x1 minus x3 times f2 here comes from this matrix form. All right. Then you can have A B, and C by substituting F1, F2, F3 in the first column, in the second column, and in the third column. Understand or not? Okay, you can try. You can try to evaluate A, B, and C there. Okay, and if you take a look at the equation here, there is derivative delta there, where the delta is given by the determinant of this, where it is referred to this. Okay, if you can evaluate one by one, it can be written as this one. All right, clear everyone? So this is just the proving process here. Okay, so now once you obtain the values of A, B, and C, then the minimum point of the quadratic function is given by what? Okay, theoretically it is given by minus b over 2a. Remember, in quadratic function, we have ax squared plus bx plus c, right? When a greater than 0, then the minimum point is minus b over 2a. So in quadratic interpolation, it is given by function here. The function x here has a minimum at x equals to minus b over 2a if a greater than 0. All right, if a less than 0, then you can find the maximum point. So as a result, minus b is given by minus this one, this expression, over 2a, so 2 times with this a, and then we have the minimum for fx can be calculated by minus b over 2a here, which is given by delta there. Okay, clear? We have a quadratic function. Okay, let's say we want to find 3 values of distinct points in quadratic function. Then we can evaluate the function one by one, a, b, and c. Then theoretically, the quadratic equation has a minimum point at minus b over 2a. Then we can evaluate that minus b over 2a from the equation that we obtain. So it is given here by delta. Okay, so this delta is a minimum point of minus b over 2a, where a greater than 0, and this is your a. All right, clear? So up to this point, everyone's clear or not? Any question? You can try to prove the A and the B and C here by solving the Cramer's rule of ABC there and simplify, and then you can get A, B, and C, and also the delta there. And then by using minus B over 2A, we can find the minimum value of the quadratic function here. Okay. Okay, so any question before we proceed? Okay, so now after getting the value that minimize the function, okay, one of them will be discarded and will be replaced by delta. The iteration is continued until the accuracy is obtained. Okay, so basically we have ax squared plus bx plus c, only one x, right? We are using x1, x2, and x3 here as a 3 distinct points in order to approximate the minimum value. Okay, so we are going to have a number of points in determining the minimum value. So now, once you obtain, after getting the value that minimize the function, one of them will be discarded and will be replaced by delta. The iteration is continued until the accuracy is obtained in terms of epsilon. All right. So later we're going to take a look at this. How can we apply to discard the value of which minimize the function and replace by delta. Okay, because this is an approximate solution, so we are going to have more than one variable, but original function is in terms of one variable. Okay, and this method can also be used to find the minimum of fx at the points along the line x naught plus lambda d for fx, where x naught is in initial point. So this is for cubic. Okay, later we are going to take a look cubic interpolation. Okay, instead of finding the minimum point one by one by using minus b over 2a and delta here, then we can also use to find the minimum of function at the point along x naught plus lambda d. Okay, where this is for cubic interpolation method. All right, so as for today, let's take a look at quadratic interpolation method first. Okay, so now let's take a look. First, you need to determine the initial point. Okay, your initial point is x1, which is equals to a, and the step length h, where you can find x2 by equals to a plus h with an accuracy epsilon. Okay, in quadratic interpolation, we have initial point, we have step length, and also the accuracy. So start the process with the first three numbers. Okay, so first you have x1 and then you have your x2. Find f1 and f2. If f1 less than f2, then x3 equals to a minus h. If not, x3 plus 2h. Okay, if it is for maximum, okay, this is for minimum, then just reverse this. All right. So now you have what? You have your x1, you have your x2, you have your x3. So we start with the first three numbers. Okay. One, and then you can find your f3. All right. Next, find the value of delta, where that delta can be used as S4. Okay. Where does this delta comes from? This one. All right. How can we find delta here? So now you have x1, x2, x3, and x4. Okay. We need to find f4 and test the minimum. Okay. So how to test the minimum point? Right. In order to test the minimum point here, you need to arrange the values of fx in the ascending order. So you have your xi, you have your fi. Initially, you know that x1, x2, x3, and x4, right? By calculate the value from step 2 and step 3. But now in step 4, you have to arrange this in ascending order. So your x1, x2, x3, and x4 in step number 4 maybe differ to the previous values. Understand or not? Later we are going to take a look at the example. Okay. Once it is sorted, then you need to test. Okay, you need to test. If the difference between the lowest and the second lowest is less than epsilon, then we terminate the process. So lowest and second lowest means that what? Means that x1 and x2. Okay, so if x1 minus x2 less than epsilon, then we should stop the process. Okay, if not, if we did not terminate, right, we would discard the point with the highest function. Okay, in step 4, if we are not able to terminate the process at step 4 here, we would discard the point with the highest function value, which is what? Which is highest function here is x4 here, because it is sorted, right? So we should discard the point with the highest function and then return to step 3. Okay. In step 3, we need to again find the delta there. Okay. Clear? Okay. If, however, by retaining the value of the highest function, we need to put a definite bracket on the location of minimum, then we should indeed retain the value and return to step 3. Okay, so this is the case if you don't want to discard the highest function. Okay, you can do it, but usually it is advisable to discard. But if you don't want to discard, so theoretically it can do it, we can do it, but you need to put a definite bracket on the location of minimum. All right, let's say x4 here is the highest, right? Okay, previously you know that we need to discard the highest value, the highest function value, but now we don't want to discard the highest function, but what we can do is we can put the definite bracket on the location. So as you can see here, you know that the minimum is here, right? Okay, so in terms of minimum point, you know that this is the bracket that you should consider, even though we need to discard x4, okay? But if you want to remain x4, you need to put the definite bracket in the location of the minimum, where the minimum is x1. So you discard what? You discard x3. So same process. Instead of discarding the highest value, you discard the point which is outside the bracket of the location of minimum. Okay, it can either be x2, it can either be x1, it can either be x4. Okay, but you have to understand about the location of the minimum. Okay, and once you identify the bracket, again return to step number 3 here. Okay, delta. Clear or not? All right. Okay, so now let's take a look again. First, you know your x1, you know your x2, right? And then you check f1 and f2. If f1 less than f2, you choose x3 a minus h. Okay. If your f1 greater than f2, you choose your x3 a plus 2h. Then find f3. Once you have your x1, x2, and x3, then you can find your delta, where the delta is x4. Now, in step 2 and step 3, you have x1, x2, x3, and x4. Okay. In order to test the minimum, you need to rearrange. All right. Rearrange accordingly to the order, ascending order. Okay. In the arrangement, we have to check first if the lowest function and the second lowest, which is x1 and x2, if the difference of x1 and x2 less than epsilon, then the optimal solution is obtained. We should stop the process. But if it is not less than epsilon, we have two options. First, we just can discard the highest function value, which is x4, or you need to identify the location of minimum and put the definite bracket. Okay, so for to make it standardized, all right, let's choose option 1, okay, where we discard the highest function value, okay. But if you choose option 2, it is not wrong. It is also doable, but you need to understand where is the location of the minimum. Okay, understand or not? So now, once you can obtain the bracket, or once you discard the highest point, again, you should return to step 3 until you should get this. Okay, when it is less than epsilon, then just terminate the process. All right. Okay, now in step 6, okay, we just need to continue the process. But if the accuracy is set too small, okay, maybe x1, x2, x3, and f1, f2, f3 will be very close together. Okay, and delta may well become totally unreliable. All right, so to overcome this, we should use this. So instead of using this delta, we can also use this. Okay, no different. But why we need to do this? Because we just want to avoid a very small difference between the point. Okay, why? If you select the smaller difference between the points, maybe it takes us quite a number of iteration before we reach our optimal solution. Okay, remember, in reaching the optimal solution, we always need to check the values of x1 minus x2 less than epsilon. Okay, if they are close, then maybe the difference is not as big enough, so we can have quite a numbers of iteration. All right, is that clear? Okay, so this is the quadratic interpolation method. All right. Anyone has question? Okay. That means, let me find one example for you. Okay, let's do this together. What is our first one? Right, look at your notes and the algorithm given. What is our first step in iteration number 1? Okay, let's start with iteration 1. What we need to do for each iteration, all right, for each iteration it should follow all steps 1, 2, 3, 4 until 6 here. Okay, so in iteration 1, what is our starting point here? Okay, let's do this together. What should we start with? Come on. Right, so your x1 equals to 1, right? And then your x2 is equals to a plus h, which is 1 plus 0.5. And then you can find your f1 and f2, okay? By using the function here. What is your f1? What is your f2 there? Okay, so f1 is 1.6321 and f2 is 4.2769. Okay, then we need to find x3 by considering this. So let's take a look at this f1 and f2. So now you can see that f1 less than f2, and then when f1 less than f2, your x3 should be a minus h, which is 0.5. And then you can find your f3. What is your f3 there? All right, what is your f3? So minus 0.1065. So that is your f3 and your x3. Once you obtain all x1, x2, x3, f1, f2, f3, then you need to find x4 by using delta. Okay, clear now? So you need to calculate this delta. Just substitute all the values. Okay, find it. Oh, sorry guys. This should be exponent to the power of x. Okay, let me the correct answer here. Sorry. F1 is can check again. Thank you for the answer, but I just changed the function here. We can also use the previous function, but maybe I don't know about the number of iteration, right? So let's just change the function there for our class session here. Okay. All right, what is your X for? Try to find X4. Okay. X4 and F4. All right, then calculate first. Try to obtain the answer. All right, got it? Okay, so maybe there's a decimal operation there. Okay, both are correct, right? So now let's just use 2 there. Oops. Okay, so now what we need to do, okay, let's just use your value. Okay, what we need to do is what? Once you obtain x1, x2, x3, and x4, you have to test the minimum. Okay, arrange the values of fx in the ascending order. Okay, check the value of fx in the ascending order. So now we have what? We have xi, we have fi. Okay, the smallest one should be what? Smallest one should be minus this one, right? Minus 1.1487, okay, which is come from x3, 0.5. Okay, and then the second lowest should be minus 1.0438, which comes from x4, 0.0472. Okay, and then the next one is minus 0.7183, which comes from x1, right? And then the last one is 0.0183, which comes from x2. So now you have to arrange accordingly to the ascending order of what? Arrange the values of fx. Okay, so this arrangement consider the value of fx. Lowest one, second lowest, the third lowest, and the highest one. So now this is your x1, x2, x3, and x4 in the next iteration. Okay, in the next step and iteration. So next, once you arrange, what you have to do is to test the condition. Okay, so in xi and fi here, you should test the condition of what? The first one is what? The first one that you need to test is the stopping criteria. Is it less than epsilon or not? So for this case, you should have what? x1 minus x2. Check the condition. Okay, check the condition here. x1 minus x2 equals to what? What should you get? Zero point 0.45. Which is greater than epsilon, right? Because your epsilon is 0.001. Okay, 0.01. 0.001. Okay, so it is greater than epsilon, then you need to continue the iteration. But now we have to have another condition here. Okay, the first condition is to check the stopping criteria. The second one, okay, if we not terminate the process, we should discard the point with the highest function and then return to step 3. So the highest function is x4. Okay, so we discard this. Then in your next iteration, x1 equals to 0.5, f1 equals to negative 1.1487, x2 0.0472, f2 equals to minus 1.0438, x3 equals to 1, f3 equals to minus 0.7183. So in iteration 2, you have your points of x1, x2, and x3, f1, f2, f3, and you just need to find your x4 by again calculate the value of delta and repeat the process until you reach the solution point where x1 minus x2 should less than epsilon. Understand or not? Okay, please proceed until you should reach iteration 5. Only 5 iteration. Okay, please proceed. Then we discuss. Okay, so this is the correct one for epsilon equals to 0.01. So as you can see, the smaller the epsilon, the longer the iteration. But all of the solution that you obtain here are all the approximate solution. Okay, we cannot say that that is right, that is correct or wrong. Okay, but this is only approximate solution where we just need to find the approximate value of the extremizer. Okay, anyone want to share another one? Some more? I think for this one is epsilon 0.01. If you use 0.001, I think you can get up until iteration 5 only. Any question for this method? All right, we got the same answer. Okay, good. So now we have done with quadratic interpolation method.